Today's topic is photoelectric effect and duality of light waves. Now, what are the ways in which you can extract an electron out of a matter? What are the ways? One way could be thermally, you heat something to very high temperature so that electrons is emitted. Second, you can do it by field emission. By electric field. You may have very strong electric field, which may cause the electron to emit from the material. Third is photoelectric emission. Our today's topic is will be concentrated more on photoelectric emission. Now, what is a photoelectric emission? For example, you take a metal plate onto which you incident some light rays. Now, what happens is light rays have got energy into it. And due to that energy, the electrons which are lying everywhere in this metal get excited because of these rays. And they excite it so much that they tend to come out, emit from the body. But it is not as simple as that. They're not so free that somebody gives them a slight excitation and they come out. No, it is not so simple. There are certain hurdles in between. This we're going to see. Okay. First thing is, what is a photon? It is believed that the light rays that you incident on any metal plate or some other material carries energy. Okay, but it is not continuous energy. It is not a continuous stream of energy. Rather, it is quantized. What do you mean by quantized? For example, you take a garden hose to water your plants. You connect your water hose to a tap. And when you spray, you get a continuous source of stream of water. Yeah. Now, have you seen a lawn sprayer? How it goes? It doesn't throw water in one stream. Throws a stream, then stops. Throws a stream, stops. Throws a stream, stops. Very, very similarly, the energy in a light ray is packed in packets. number of packets. Each packet is called a photon. And the property of this photon is that each has got fixed amount of energy. Primarily depending upon the frequency of the light radiation. So all will have similar, and the energy possessed by a photon is equal to h. H is Planck's constant. Nu is the frequency of radiation. Okay, so we learned one thing, that the radiating rays, radiation rays, they carry energy, yes, but not continuously. They carry in small pockets. These pockets or packets are called photons, which carry a fixed amount of energy. And this amount of energy is fixed as per the frequency of the radiation rays. All right. Would you be surprised if somebody says that these photons can have momentum? Huh? A packet of energy having momentum? Yes, it does have momentum. And the momentum is defined as energy divided by c, where c is the speed of light. Okay. So if I write momentum as P, which is equal to energy by C, and the energy possessed by a photon is h nu by C, and nu can be defined as, again, nu is nothing but wavelength C also equal to C. So there are many ways you can define P in, but basically the basic formula is that P is defined as energy of the photon divided by velocity of light. And one thing you have to be very, very careful. This formula is applicable only to photons and not photoelectrons. Photoelectrons are the electrons that are emitted on account of photons falling on a metal surface, which causes the electron to come out. And the electrons that come out are called photoelectrons. So this treatment is applicable only to photons and not to photoelectrons. You have to be very careful. Okay. Now, what is the work function? We have seen a photon which has this much of energy. This one's energy is imparted to, is given to electron. But is this energy, this step is sufficient for the electrons to leave the metal? No, it is not. Because the metal tried to hold the electron, and the electron has to work against that holding phenomena and spend some energy in doing that. So the energy that was imparted to photon, to electron, which was h nu, a part of is used in overcoming, let's say, a work that is to be done to overcome is coming out of the metal, which is called work function. So once it has spent this much, once a photoelectron has spent with this much energy, it has spent this much energy to come out. This is the balance energy with the photoelectron. And this is we call as kinetic energy, balance kinetic energy, so much. Now with this much energy, it can come out. It is possible to come out. Okay. Now, before we see anything, let's see an experimental setup. This is a tube in which we have two electrodes. You apply some voltage to it. So obviously, this is what we do is we attach negative to this and positive to battery. So this portion becomes cathode, the negative part, and this is anode, the positive portion. Now, when some energy is incident on it by way of a radiating wave, radiation, an electron tries to come out. And by the time it has come out, it is left with this much of energy. All right. Now, to the opposite end is an anode. Now, what it can do is, if it is positive, it will assist the electron to come towards anode and hence set up a current. This is conventional current, but electron will flow like this, which is the opposite of conventional current. All right. Now, instead of making it positive with respect to cathode, what if it is made negative with respect to cathode? Then what will happen is it will try to push electron back. It will resist electron to come to this portion. All right. Now, if we can determine a voltage when, if applied to an anode, will not let electron come near to it. That voltage is called stopping voltage. When this happens, when anode is negative with respect to cathode. If a reverse voltage is so much is applied, which completely stops the flow of electron, this is called stopping voltage. If this is positive, then it will assist in the flow of electron. Now, if we plot the node voltage against this current, then what we will see is that as we increase the voltage positively, the current increases and becomes steady at certain point. Why it becomes steady? Because whatever electrons were emitted at this stage, they have all been picked up here. So there is no more electron to come by. So whatever was possible has been attracted. So this portion becomes saturated. This is our saturation current. And you see, if this voltage is dropped and dropped so much that at this point, if I say this point, there is no current at all, and this voltage is negative. So this voltage will be called stopping voltage. Okay. Now, we've seen that this is the kinetic energy which is left after the photoelectron has spent some energy in coming out. So what can be the value of K? K can at the most go to 0. That means once it comes out of after spending work function, says, sorry, I'm all finished. I have nothing more with me. Okay. So, K is equal to h nu by work function. K can at the most go to 0. All right. When this goes to 0, this means my h nu is equal to work function. And what is my frequency? H. This particular frequency, if I go below this frequency, this work function, this wave will, this photon will not have enough energy to overcome this work function. So in order to just overcome this function, you have to have the radiation has to have a frequency which is at least this much. So this is called threshold frequency. Below this frequency, no electron will be able to come out. It may be sufficient to excite the electron, but it will not be sufficient to overcome this work function. And similarly, you can express this in terms of lambda also. This is H. This implies that CH is equal to lambda 5. Implies lambda is equal to CH by 4. Again, this lambda is called threshold If we have a wavelength greater than this, then it will not be able to cross this threshold function. Now, if we see this example, let's see this anode was made negative with respect to cathode, then what will happen? The negative anode will try to desist electron coming near to it. In case it has got sufficient energy, still it will try to come to anode on its own energy. It may just reach. Now let's see a condition when this electron has got just enough kinetic energy to be able to overcome this negative field and come to anode. In that case, what happens is the kinetic energy that the photoelectron had just after emission, just after taking care of work function, then this much of energy was used to overcome the electric gradient. And finally, whole of K was spent in overcoming. Whole of K was spent in overcoming the electrical field, which is charge into voltage. So this much energy, this much work the electron had to do just to be able to reach anode. And it had just enough energy to reach anode, and after that it has the final energy, it was left with is 0. So in this condition, what happens is, if we write this as K max, which it had earlier. So K max becomes EV 0, right? Under this condition, this becomes our stopping voltage. Now you can evaluate it in many forms, that EV naught, which was equal to K max, and K max was actually H nu minus, or you can write, if you don't want frequency, if you want to put it in terms of lambda, same thing. Or we can write U naught is equal to C again. These are various forms you can write the stopping voltages, but both are, everything is basically same. Stopping voltage. Now there is another phenomenon called what de Broglie said was that if you take any wave or any radiation, you can define a term called lambda, which is mathematically defined like this. This is the Planck's constant. This is the momentum. Now this would be equal to P will be equal to where M is mass, A is kinetic energy, which is equal to. Now, in terms of photoelectron, you can very, very easily understand that this would become the mass of the electron, this thing, and V will be the velocity of the electron. So a moving electron will have momentum, and if you divide h by the momentum, whatever figure you get, we call it as de Broglie. Now this is basically as far as photoelectric effect is concerned, but our aim is also to see why light behaves like wave as well as particle. This is called dual nature. Which are the phenomena which shows that it a light behaves like wave, and what are the phenomena which shows that it behaves like a particle? First and foremost is de Broglie argued that radiation show dual nature. If radiation shows dual nature, so should then matter should also show dual nature. Why dual nature? De Broglie is defined that even if you have a photon, you can associate momentum to it. Now, wave nature is amply proved by a phenomenon called interference. In interference, we always talked about, A1 sine omega t plus x or minus x, etc. And another maybe, and then we let them interfere with each other and we got some result. And what are these? These are wave functions. So light behaves like a wave function, which is amply proven in interference. That is one. This is again proven in diffraction. Then polarization. In polarization, we know that if you take filters, then you can cut off some component in a particular direction, which is possible only if it were behaving like a wave. Okay? But this wave nature could not explain the phenomena of photo wave function could not explain this. So all these amply clearly explain that light behaves like a wave without beyond doubt. And another argument is that if the intensity radiation is more, then more energy should be absorbed by electrons, which means the kinetic energy of electrons should increase with intensity. I mean, it is quite obvious. The more the intense radiation is, more energy is going to be absorbed by electrons. And if more energy is going to be absorbed by electrons, it will be only in the form of kinetic energy. So electrons will have a lot of kinetic energy. If the intensity is more, which means that more the intensity, more is the kinetic energy of the electrons. But this is not supported by experiment. Secondly, even if the radiation are very, very feeble, and we allow large amount of time to pass by, let's say there is this metal and a very low intensity or feeble, whatever you call it, radiation is incident on this plate, then a common sense says that, okay, electrons may not come out immediately. Let it soak it for a while. And if you let sufficient time pass by, then photoelectrons will come out. But doesn't happen. Why? We have seen threshold frequency. What does it say? If the frequency of the radiation waves are below certain value, no electron will come out. You may keep shining that radiation for years, no electron will come out. So again, this phenomena is not explained by wave nature. Now, what supports in part? What is in support of? Particle nature? Or rather, what are the phenomena which support that light does behave like a particle, which is photoelectric? It says that everything is quantized, packets. Photons. They're packets. And Einstein also proved that momentum can be associated with photons. If you can attach momentum to photons, and momentum is purely on account of particle nature. We are talking about mass and velocities. So Einstein did prove that light can, a momentum can be associated with photons. So this is a direct consequence of saying that light is behaving like a particle.